So, hypothesis testing. And when I talk about hypothesis testing, then I mean hypothesis testing in a statistical sense. If you compare, for example, the typical scientific hypothesis, it's slightly different. A scientific hypothesis asks the question about, for example, is the BCL1 gene involved in the development of breast cancer? And then you do your experiments, whatever way, and then you usually come up with an answer or not. And from this hypothesis, you go on. Statistical hypothesis is slightly different, but what we will see is that it works in a very similar way, although it's quite formulaic. Your hypothesis that you will formulate always have the same text. It's always the same thing. Can I quickly have a show of hands? How many people have done hypothesis testing? Not everybody. Okay, no, that's quite good. So hopefully for some people there will be something new. Now, with hypothesis testing in statistics, let's just simply try a simple example. Let's say we have a certain population. This is this population here, pop. Let's call this pop1. This population has parameters, as I said, parameters, population. So it is characterized by a mean, by a standard deviation, and we can take samples from that. So we can take a sample here, and these samples are characterized by their mean, and of course by their standard deviation. So these are the statistics of the samples. So far, so good. Nothing terribly exciting about that. Now I can take a second population. So that's my pop2. And again, this pop2 is characterized by the parameters, and I can take samples of that. So here that would be x, c, standard deviation c, xd, standard deviation d. Nothing really that, makes your juices flow. Just from looking at that, would you say that the populations are different from each other, just looking at it that way? Are they different? Do they have the same mean? Do they have the same average? Well, the way I've drawn it, no, definitely not. I mean, even I can see that here's a population, there's a population. It doesn't look like they've got anything to do with each other. So, very clearly, it's not a big problem. We can say the populations are different. Okay, now here is a question for you. What would happen if, for example, I take the sample here, XA. What have I done? That should be an A, of course. With a standard deviation A. And I take a sample let's do it like that. That's x bar c and standard deviation c. Do these two samples, as I've drawn them here, do they represent the same population? Anton goes like that. Do they represent the same population? What would you say? Do they belong to the same population, these two samples? Well, the way I've drawn it is they are really far apart from each other. It could be, there could be a slight chance that they are from the same population, but the way it's drawn, it's rather, they don't belong to the same population. Because I sort of have taken it from here and from here. But still there could be a slight chance. Okay, let's go to a slightly more difficult question. What about my sample A? That's my sample 1, sample A. And here's my sample B, or C, whatever. That's the red one. Are they now from the same population? Is it more likely that they are from the same population? Yeah, it's getting more likely. The probability that they are from the same population is getting bigger. I could represent these two samples also with this thing that we've done in the last week, where we looked at the confidence interval. So, for example, I've got my mean here, and I can draw my confidence interval. That's the Ci. And I can do that for the red one as well. And this is the red confidence interval. I don't know whether you see the colors, but the right one is the red one. What does this confidence interval actually, what did it tell us last time? It told us something about the likelihood, the probability that the true population mean is actually within this confidence interval here. So the population mean for this, which the sample represents, is somewhere in here, somewhere. Yeah? And likewise, for the black sample, the population mean is somewhere in here. Now, we have, obviously, a range where the population mean for this sample lies, and a range where the population mean for this sample lies. And obviously, one population can't have two different means. It's not possible. So what would you say? The way it's drawn here, do these samples represent one population or two different populations? What would you say? Is there one population, or do they represent two? Two. Why? You're absolutely right, but why is it two? There's no overlap. So this sample here, the black one, must have a population mean somewhere in here, at least 95% of the samples, if I did that 100 times. The red one would have a population mean somewhere in here. We have two population means. That means we have two populations. That means these samples are coming from different populations. These samples are representing different populations. Yeah? Does that make sense? Now it's getting interesting. What about we have this case? That's our sample 1 and that's our sample 2. Do they come from the same population? Is there only one population, or are there two populations? What do you reckon? Who thinks it's one population? Hands up. Okay. Who thinks it's two populations? Hands up. Who thinks, when is he going to stop about that crap? And because I'm not ever going to use that, hands up. Usually there's somebody. Well, if you said there's one population, you're absolutely right. If you said there are two populations, you're absolutely right. It can be either. It depends on the confidence intervals. So, if we have, for example, oops, that should be black. Let's say we've got a confidence interval like that for the black one, and we have a confidence interval for the red one like that. It could very well be that the true population mean for the red one is somewhere here, and the true population mean for the black one is somewhere in here. So at this point we can't really determine whether it is just one population mean, which could indicate that it's one population, or that there are two population means, which actually indicates that there would be two populations. Right? So in this case, we don't know. And however, there is quite a nice way of dealing with that. Because what we can do is we can actually set up what is called a hypothesis. Hypothesis, in a way, would be there are two different populations, or there is one population only. And both samples represent the same population. And statisticians always, they're a little bit like lawyers. They want everything spelled out so that it's completely unambiguous. And therefore, they came up with the idea of spelling it out really like in a contract. So the first thing that the statisticians do is they say, we have what is called the null hypothesis. This null hypothesis is, oh dear, that sounds healthy. The null hypothesis is usually abbreviated with an H0. And this null hypothesis is very, very formulaic. It's always the same thing. And this null hypothesis says the two samples represent populations whose means, and very often we are talking about means in this case, whose means are not different. The only difference between the samples is caused. What could cause this difference? Where do we see a difference? Sampling error, exactly. Every time I take a sample, I make a sampling error. I can't avoid sampling error. So this the difference between these samples is caused by sampling error only. Okay? Lots of text, but these are the lawyers. And every day you are dealing with lawyers. Every day you lie, actually, to lawyers. What is the most popular lie in the world? Sorry? Loud? Who said it? Somebody? Don't add my homework. Oh, no, that's completely at the bottom of the list.
I've read the terms and conditions.
Absolutely right. I've read the terms and conditions. Nobody reads the terms and conditions. You just click on yes. Right? And I agree. This is the most common lie in the world. In this case, it's a little bit like read the terms and conditions. It's always the same wording, but I want you to really remember that. And the way you remember it is H0 or H0, you see this little O, you see this big O in here. Yeah? There's no difference between the samples. That's sort of the short version. There's no difference between the samples other than caused by sampling error. Okay? Happy with that? I want you to remember that. I will ask that in your exam. You might encounter this in a test. Let's put it this way. Okay, so we have a null hypothesis. We also want to have another option. It's always good to have options. And therefore, the lawyers, other than I have read the agreement, you also usually have another button there where you say, I don't agree, but nobody is pressing that because you won't get what you want. So in statistics, you also have this get out clause, which is called H1. This is the alternative hypothesis. And the alternative hypothesis is exactly the opposite of the null hypothesis. But we need to be a little bit careful with that. The alternative hypothesis basically says the two samples represent populations whose means are different. The difference write it properly, between the samples is caused by what? Sorry, loud? Absolutely right. I couldn't have phrased it any better. It's caused by the sampling error. And another effect. And it's this and that there is something else in it. That's important. So that's our alternative hypothesis. I said we need to be a little bit careful with this alternative hypothesis. The reason why we need to be careful is it could be, the way we formulated it says there is a difference between the sample means, but we don't, in a way, commit ourselves of saying one sample, one particular sample, is larger than the other one. So, this actually could mean population 1 is larger than population 2. Yeah? Or it could also mean population 1 is smaller than population 2. We haven't committed ourselves. It could go either way. All we know is it's different. Why is it not showing anything? That's interesting. Oh, wow. I have a breakdown. Sorry about that. Anyway, with this alternative hypothesis, it could mean population 1 is larger than population 2, or population 1 is smaller than population 2. All we have committed ourselves to saying is there is a difference between them. So I have basically two options here. Two options. And I want you to remember this 2 here. If I'm a little bit more, how shall I say, braver, I could say I commit myself and I say, right, I know there is a difference, or my hypothesis, my alternative hypothesis is there is a difference. So H1, and I'm not writing it down again, there is a difference. Which is caused by sampling error and another effect, and population 1 is larger than population 2. How many options do I have now? Just one. Yeah? So one option. I could say population 1 is larger than population 2. Or I could also say population 1 is smaller than population 2, but I have determined myself. I have only one option here. Makes sense? We have one option compared to two options. And we find this has an impact on the way I do my tests. Let me quickly illustrate that. We discussed the normal curve, the standard curve. So here was the mean. And this here is 2 sigma. That's also 2 sigma, so that's minus 2 sigma and plus 2 sigma. What's the percentage of my data that is in this range here? What did we say? What's the percentage of data in here? 95%, exactly. So 95% our data should lie in this range here. Or in other words, if I pick just a number, a datum, singular of data, if I just pick a datum, there's a 95% chance that it lies in this range. In other words, there is a 5% chance that this thing doesn't lie within it. So I have a 5% chance that my data are lying outside. Let's say that a sample is outside this range, outside the 4 sigma range. 5% outside. So my H1, my alternative hypothesis says, there's a 5% chance that the data are not in this 95% range. Does it say anything about larger or smaller? Obviously not. So what's the range here? What is this probability here? How much of my data would lie in this yellow bit? 2.5. Can you see that? Probably not. So it's 2.5% either way. Yeah? So in a way, if you look at that, it has this curve has 2 tails, if you like. So one tail and the second tail. So when I say my data are outside this 95% range, I don't commit myself and I don't say one is bigger than the other. So there's a 5% chance that it is outside the 95%, and therefore this is called two-tailed. So two-tailed, 5%. Because it could be either smaller or bigger than this 4 sigma range. But if I say one is outside, one is larger than the other, I determine that, one is larger than the other, and I say I want it 95%, then I've committed myself, and it looks probably something like that. In this case, it will nip in a little bit here with the, when I say sample is larger. So this would be, I only look at one tail, and that would be one-tailed. basically, the reason why I harp on about this, about two-tailed and one-tailed, there are differences in how you calculate or how a statistical program actually calculates values. And you need to be aware of that. So, what do we do? I want to compare two samples. And to give you a practical example, you measured the BSA concentration in the practical, and I pick 3 students who had the same protein number, let's say 15.5, 14.8, and 13.2. So that was the BSA concentration that they gave me. And then I pick 3 other students, so BSA concentration, and they are 19.8, 21.3, and 20, and no, let's say 17.1. Did these 6 students use the same BSA? Did they use, or in other words, is BSA concentration 1 the same as BSA concentration 2? Might be, might not be. What do you think? Sorry? We don't know the confidence interval. Yeah, that's right. We could very easily calculate that with the standard deviation times 2.5. Yeah, you know the rule of thumb. And then we need to do a test on that. I'm not giving you the equation for this test because nobody in their right mind will ever do this kind of test by hand. We have computers to do that. And in an exam or so, I will not expect you to do this test by hand. So don't learn the equation. Life is too short. And Einstein once said, never memorize anything that you can look up. So what the heck are you doing here, by the way? But that's a different story. So, what we are going to do in the first place is we need to formulate our null hypothesis. That's the first thing that you always do. So formulate the null hypothesis. And I do it in the abbreviated form. The null hypothesis says the means of the 2 samples are, thank you, not different other than caused by sampling error. The English is lousy, but who cares? In this case, there are no lawyers. You know the story about the lawyers when God and Satan had a dispute about a fence. And allegedly Satan built the fence too far on God's side. And God said, Satan, with all, with the best will in the world, but you have to move the fence. And Satan said, or what? And God said, I will sue you. And then Satan laughed and said, and where do you think you will find the lawyers? Anyway, I hope there are no law students here. They are not all evil. I heard there are some good ones. Anyway, this is our abbreviated form of the null hypothesis. There's no difference between the two samples. Now, we need to formulate an alternative hypothesis. And the way we formulate this alternative hypothesis determines what kind of test we use. We can be sort of very cagey and cautious, and we can say, the means of the two samples are different because there is sampling error and an additional effect. The way I phrase it here is very cautious. I'm just saying that there is a difference. How many tails do I have here? 2 tails. It could be either larger or smaller. So, 2 tails. Or, I could be braver, and I could say, the means of the 2 samples are different, and the mean for the second sample is larger than the mean for the first sample. How many tails would I have? 1. Yeah? Does that make sense? So, please be aware of these different tails. 2 tails, non-committal. There is just a difference, which is not caused by the standard, by the sampling error. 1 tail, there is a difference, and one of these samples is, and I have to name which sample it is, one of these samples is larger than the other one. So how do we measure that? Well, again, we can use what is called a probability. And coming back to this beautiful standard curve, I can say actually, what is my probability that my sample is in these 95%, for example? Or what is my probability that the sample is in the 68% or 99.7%? I just have to choose what probability it is that I want. So what is the probability that my sample is in there? And you can ask a computer to do this calculation for you, and it will give you what is called a p-value. This p-value stands for p, probability. Now, I need to define what my range will be in this case. So if I say, I want to be sure that my sample falls within this range here, where 95% of the data are, or in other words, I will allow 5% of the data to be outside this. That could happen. This is my uncertainty. This is the significance level. So this is this alpha. And I say, I accept that 5%, for example, 5% of my data are outside. Now, if the probability that the computer gives me, if the probability is smaller than this alpha, so for example, I pick a sample over here. This is probably 3, 4, 5 alphas, 5 sigmas out. How likely is it that this belongs to the same curve? It's not terribly likely. So this probability is fairly small. It is smaller than this alpha. Would I say that this sample here, that I picked here, belongs to this curve? No. Would I say that there is a difference between this one here and the data represented in this curve? Yes, I would say so. There is a difference, and it's not just simply caused by the sampling error. There must be, it's probably something different, completely different. It's, for example, these data represent the length of mice, and by accident I measured a rat, which is much bigger. Yeah, so this would be this one here. So I would get something different here. So if this p value is smaller than this alpha, and alpha very often is set at 5%, I have to boot out my null hypothesis. The null hypothesis is there's no difference. But if p is smaller than alpha, then this null hypothesis is not right, and I have to accept the alternative hypothesis. On the other hand, if p is larger than alpha, I can accept h0, and I don't have to think about h1, because if I accept h0, h1 can't be right. Does that make sense? So your criterion is p smaller than alpha or not? If it is smaller, then the samples can't represent the same population. And there is a simple way of remembering that, and I want you, I always need to look for silly things that make things more memorable. And you have to say that, the next two sentences, you have to say that with an Australian accent. I can't remember the mnemonic now. If p is small, if p is low, that's the way. If p is low, which means lower than alpha, if p is low, h0 must go. If p is high, h0 can stay. Right? So, p low, h0 goes out of the window. The samples are different. P is higher than alpha. H naught can stay. I've been inspired by I'm a Celebrity, Get Me Out of Here, which I have to watch every night because my son is addicted to it. So if P is high, then we accept the accept that the samples are the same. So if I give you P equals 0.5, alpha equals 0.05, do we accept or reject the null hypothesis? P is high, so null hypothesis can stay. Very simple. Yeah? I want you to remember that. And this P is not necessarily tied to a specific test. It is just simply a probability that your calculator can give you. Yeah? So, as I said, if I give you a P, and an alpha, are the two samples the same? Are the two samples the same? Yes? Yes or yes? They are not the same. P is low. P is so low that your computer can't even show you how low it is. P is so low, so it's very, very unlikely that I picked it from just the same thing, which just differs by the sampling error. So the two samples are not the same. On Monday, I show you how you do that on your spreadsheets on Excel. Is anyone here who is using a Chromebook? Chromebook users, hands up? Okay, that's fantastic. That's absolutely brilliant. Anyone using Excel here? Yeah? Everybody else is using Excel. Anyone using anything else? Sorry? Everybody using Excel. Fantastic. Then I'll show you how it works in Excel. I shall see you on Monday.